Hello again, everyone. My name is Chris Dorn. I'm a technical sales specialist for Global Test Supply. Thank you for joining us today via our webinar via the Global Test Supply University. Today's topic is pressure calibrations with Fluke. During the presentation, I'm going to ask you to kindly mute your microphone. The presentation should last anywhere between 40 and 45 minutes. And at the end, we'll have time allotted for some Q&A as well. So we encourage you throughout the presentation to use the chat feature and submit any and all questions that you may have. Try and take advantage of having an expert like Ken connected with us today to answer any and all questions. So Global Test Supply has been working closely with Fluke for many years. We pride ourselves on being a leading distributor of Fluke. This is the result of our dedication to offering you our product expertise, service, and competitive pricing. Today's webinar is presented by Ken Reeves from Fluke. Ken is Fluke's territory manager, sales rep, based in Alberta, Canada. He has over 31 years of technical test equipment sales, which includes over 20 years working directly for Fluke. Ken, I will turn the presentation over to you.
Thank you, Chris. Good afternoon, good morning, everybody. We'll get right into it. We've got a fair bit of content to cover today, and hope you find it valuable. Let's talk today about the topics that are highlighted here. I won't run through them, I'll let you read them. But the goal of the session, by the time we're done our hour here together, a little bit less than that, will hopefully give you some practical information about how to deal with your pressure calibrations, things to consider that you may not have already considered, and ultimately walk away with some tech tips and maybe some new technology. Without any further ado, let's just take a quick review of what is calibration. Calibration in general is the comparison of a measurement device as an unknown against an equal or better standard, which is a known. So as we see in the picture there, we've got a person doing a calibration. They've got a device mounted on a pole there. That's their equipment that they use to run their plant. And they've brought a piece of equipment to that. That piece of equipment they brought is the standard. And it needs to be more accurate, typically 4 to 10 times more accurate than what they're actually trying to calibrate. And that's the ultimate idea of what a calibration is. It's a comparison between a value that you source or simulate or compare, and then take a look and see what your device is doing as a response. The concept of traceability is something I want to touch on now. We may make reference to it a couple of times or it may come up later, so I just want to be clear about it. Traceability is not necessarily accuracy. What traceability is a documented chain between your process instrument out in the field to the working standard, like that calibrator the person is using from Fluke, up through, say, the standards that GTS has available to them to do calibrations, all the way up to the country standard. And the traceable chain is a documented chain saying that this device was calibrated by this, and then that working standard was calibrated by a secondary, and then a primary, all the way up the chain. This traceability allows you to take accuracies from the primary standards and drive them down into your process field through documentation. Let's talk quickly about pressure. Pressure, it is described in many different ways. There's a table list of different units that you may have come across in your job. But pressure ultimately is force over area. So the force is a perpendicular force to the surface area inside a closed chamber or a closed system. And the measurement that they use for pressure in the world, the standard is Pascal, which is the SI unit for pressure. Any other pressure units that we come up with are calculated versions of what the pressure calculation is, which is force over area. So if we use the force as for instance, PSI, sorry, pounds per square inch would be force over an area. You may have kilograms per centimeter squared, which may be a metric version of it. Every single one of those have some component of force over area as a part of their description of a unit. The fun fact is that throughout the years, the F has been dropped. So as it says down on the bottom, it says similarly, pound force per square inch is normally indicated as PSI. So almost everywhere you see one of these calculations, the idea of force being removed from that calculation. The SI standard is a derived standard. That means it's not based in one of the primary measurement values that they have. Mass, meters, seconds, all being used of the 7 base units, come up with a formula for pressure. Pressure, temperature, and volume all relate to each other, and they interact and correlate with each other. So just like the pictures on the side, if we have a fixed volume and we increase the volume, increase the temperature of the green cylinder, you will see a corresponding increase in the pressure. Why is that happening? Taking us back to Science 101, the molecules themselves are actually moving in here and creating force inside this particular vessel. When the volume doesn't change, but the action of the molecules is increased, the force is increased and therefore the pressure, okay? Conversely, if we take a volume where we have a set number of molecules inside and we reduce that volume and the pressure, the temperature stays the same, those molecules will exert pressure at a higher rate across those surfaces. And that's what comes up with regards to higher pressure. Conversely, the opposite of each of these is an effect. It's important to understand because we're going to take into a bunch of best practices that correlate back to this idea of volume and temperature affecting pressure. Let's do a quick review of the different types of pressure measurements that are out there. Every application requires maybe a different way to describe the pressure that you're measuring. So here's just a few that we need to understand. First of all, there's gauge pressure. This is by far the most popular. In fact, when you ask for a 100 psi pressure gauge, what you're actually asking for is 100 psi G. And it's what it does is it measures the pressure relative to the atmosphere. So the atmosphere has pressure. We'll talk about that next. But anything that's positive above the atmosphere or negative below the atmospheric pressure is a positive or negative gauge pressure. The atmosphere itself is the force exerted by the column of molecules being acted upon by gravity. So at sea level, that's roughly 1 atmosphere or 1.01325 bar. Those two numbers are close enough to each other that bar and atmosphere get used interchangeably. Absolute pressure, that is the sum of gauge and atmosphere together. The best way for me to describe that is let's think of absolute from a zero perspective. So 0 absolute would mean I have no gauge pressure and I have no atmospheric pressure. And the best way to describe that is potentially in outer space where we have, very few molecules and there's no pressure being created out there at all. As we bring that gauge back, we start to experience some atmospheric pressure, and then if we apply a secondary pressure to that as a gauge pressure, that combination is what we call absolute pressures. Differential, if I have 2 different pressures, it's pretty self-explanatory, but if I have 2 different pressures and I want to measure the difference between those two, that is a differential. You can sometimes have some very high static pressures. So if I was making a measurement of 1,000 psi versus 1,001 psi, I would have a 1 psi differential, and that would be what my device would measure, even though I have pretty significantly high static pressures. Takes me to the next stage. What is static? Static is the relative pressure of a system, and it gets used to avoid ambiguity between gauge pressure or even differential pressures. We'll talk a little bit further about static in one of the examples that we're going to show you later. There are a few more to consider. I mentioned earlier the vacuum of space. Vacuum is the absence of molecules, and if you have no molecules, you have no pressure. Ideally, on Earth, we've actually been able to create a pressure or a vacuum, lower than interstellar space. The Large Hadron Collider has given us that ability. They pulled it to 10 to the -6 millibar. So bar being atmosphere, mil being 1,000 with 6 extra decimals in front of that. That's quite a few molecules being removed from that system. So pretty high vacuum levels. A compound gauge is a gauge that can measure both atmosphere above and below an atmosphere. So this particular gauge is pointing at 0. What it really is representing is that I'm not measuring anything above or below the atmospheric pressure, but it would measure gauge pressures above or gauge pressures below, and that's what they mean by compound. Finally, a specific version of a differential pressure is called a draft gauge. It comes from typically very low pressure differentials with very low static pressures. So if I had, for instance, a clean room application or a medical application where I didn't want any molecules coming from the outside to the inside, I would slightly pressurize my space that I'm in. And in the process of doing that, any leaks would be going out of that room, and it keeps my room clean. Those very low pressures are above that create the draft or the pressure to flow out of that room. And typically air handling systems use draft gauges for these applications. So why do we mention that? All these applications, there are pressures all over the place. We use pressure to celebrate birthday parties. We use pressure to clean the side of our houses. We use pressure to drive to work. There's pressure in our tires. And if we don't have enough pressure, usually creates a big inconvenience for us. When it comes to process measurements, pressures and temperatures work together to create reactions. And we want to control when they happen. We don't want them out of our control. So we are constantly, making measurements or providing communication back into a process like an automated process control system that will measure those pressures for us and temperatures as an example. And that raises the importance of knowing those pressures and knowing that they're accurate so that we can properly control and get the desired outcomes out of our process. So let's talk about some practical considerations when you go to select some gear and maybe some tech tips associated with that. We have one of the application notes available from Fluke, talks about 7 specific tips, and I'm going to run through them quickly for you here. So depending on the pressure that you need to source or simulate, in this case, you will pick an appropriate appropriate type of media. So typically pressures that are under 600 psi, we use gas or pneumatic pressures. The gas in that tank on the left-hand side is nitrogen, and it's pressurized to maybe higher than 600 psi, but that gives us volume and things that we can do with those pressures. There's a regulator on there to bring the pressure down to make it usable for us. If you did need to be above, higher pressures, we have a 3000 psi pneumatic, kind of like a bicycle pump from Fluke, that's available as well, just so you know that's available. But typically you don't go above 3000 psi. It becomes a safety hazard. So the tubing has to be very small. There's usually a lot of volume that's being compressed. Gases take a lot of volume to compress before they generate pressure. And the reason that we use gas or pneumatic, the positive side of all of this, is that the gases are less likely to cause contamination. So if we're just compressing the atmosphere through a hand pump, or we're using a nitrogen bottle and a regulator, those are what we call, or we would consider to be clean type calibrations. And there's less chance for contamination, which is actually one of the issues that shows up on the next slide, which is liquid calibrations. Liquid calibrations, again, they aren't preferred for pressures below 600 psi. They're typically a little bit more difficult to control, and the lower you go, they have a tendency to not work very well on the low side of things. But they do have a great capability of getting some very, very high pressures. The actual media that gets used can be oil, windshield washer fluid, hydraulic oil, water in some cases. Oil is preferred as it's less corrosive and it acts as a lubricant. But there are some concerns or some issues. First of all, the one at the bottom says cross-contamination. If I was taking a oil pressure hand pump into the field and I was calibrating, some other process, and oil in that process didn't mix well together, then I would have a contamination issue. So you just need to pay attention to that part of it. There can be other types of fluids that may be compatible that you might want to switch to, especially if you need to get high pressures. If you need to get above 10,000 PSI. Fluke doesn't sell any equipment that'll get you there. There are some specialty equipment that are available from other suppliers, but generally speaking, the industrial equipment that we sell won't get you there. Typically, what you need is very low volume and high pressures, and the tubes themselves have to be, super reinforced to eliminate any swelling and pressure reductions. And ultimately, it's a little more dangerous once we get to higher and higher pressures. So it kind of has a sweet spot between 600 psi and 10,000 psi. Let's talk about stabilizing your pressure. This is one of the biggest complaints that people have. They'll pressurize a system and then the pressure will either wander up or drift down, and they just can't seem to get it stable or get it to maintain. So let's talk about a few different of those different factors, and it comes back to that conversation earlier about volume and temperature and how they all interact with pressure. So if I pump in a certain amount of volume into a system, that is what I'm expecting to generate for pressure, but the tubing itself, as an example, might start to swell a little bit and have a reduction in your pressure, okay? If I have leaks in that system, either the pump itself can't handle it or there's a physical connection leak at a fitting. This shows up typically on pneumatic type connections because they're a little bit harder to diagnose. So you may find that you're leaking out molecules and then your pressure will continuously drop as well. There may be a case when you have pressurized a system and then it has a tendency to creep up on you. That might be an environmental change with regards to the temperature of the equipment. So if I've had a pump, like a hand pump in my vehicle, and I've taken it back into the shop and I've used it right away, as that pump warms up, so does the rest of the system, and that extra warming might create more pressure. Again, attaching it to your fluids in the process or the fluid temperature itself. Anyway, the bottom line is to try to understand the sources of these particular problems and be prepared to make adjustments, either with vernier adjustments or the conditions of the environment that you're working in. Let your equipment become stabilized to the temperature of the environment prior to making calibrations. Simple tech tips like that can help. There is an option to use lab-based equipment and bring the calibration from the field back into the lab. The lab is a very nice, stable environment from a temperature point of view. It also gives you maybe that extra level of cleanliness that you wouldn't necessarily get out in the field. So if you have an opportunity to bring your pressure calibrations back into a lab and it seems to be practical, then there's plenty of pieces of equipment out there to help you with that. You can get physical deadweight testers. You can have pumps and comparators. You also is a opportunity to use, say for instance, a pressure controller, which is a digital device that will control the pressure, usually off of a nitrogen tank. And so you get access to the full range of the pressure of that tank and have really nice digital control over the pressure and the volume changes, and do automatic calibrations. I'm going to add a little asterisk at this point in time. That pressure controller technology is very cool. And over the last 3 or 4 years, Fluke has been able to take that technology and drive it into a portable industrial piece of equipment. We'll talk about it a little bit later, and we'll give you a little overview of that particular product at the end. This really isn't intended to be a sales pitch, but I want to make sure you know that it's available out there because it really saves a lot of headaches. And again, final comment, industrial applications can be challenging. So hand pumps are typically the go-to tools, and they have a variety of different issues. Many, many years ago, I said hand pumps were like building a mousetrap. You build a better mousetrap and people will beat a path to your door. Having a good hand pump, something you can rely on, something that's quick and easy to fix, is a great piece of equipment and well worth its money that you spend on it if it's good. Let's talk quickly also about display resolution. So when I go to do a pressure calibration, there's a couple of different things that are in play. Accuracy and resolution are really two independent discussions. How accurate a device is strictly a numerical calculation. Is it 4 times? Is it 10 times more accurate? It's just a comparison between the overall accuracy specification of my standard to the unit under test. But having the right amount of resolution is a bit of a balancing act. You can sometimes walk up to a piece of equipment with too much resolution And if you have too much resolution, you might spend more time than you need to trying to get those least significant digits to settle down. We recommend that you pick equipment that has maybe 1 extra decimal of resolution to support the accuracy of your unit of your standard. And don't get too hung up on the fact that, say, for instance, in that particular image there, there's a 15.00 psi being pressurized and sensed. If I showed you 5 or 6 digits beyond the 0, they may not even have any value from an accuracy point of view, and they may just lead to complications or concerns. So that's just something to keep in mind. Contamination. The DUT, or device under test, is often very dirty. So if you walk up to your process equipment and maybe covered in steam, maybe corroded, and there may be some rust, there might be dirt and dust on it, there might have oil. There's plenty of different situations that these particular devices run under. Maybe simply covered in snow. It becomes a little bit of a guessing game as to what you're going to be up against. And if you have any of those contaminants and you're bringing a piece of test equipment to it, it's always best to clean your device under test as much as possible. So clear the connections of debris, get rid of old tape that may have been there, take the time to clean the threads, and use the correct wrenches to tighten the connections while you're making your testing. And again, use tape sparingly. This is just a small little comment. If you take a look at the tech tip on the bottom right-hand corner, it says Teflon tape is not a sealant. It's used to lubricate the threads. We have some people that'll have a leaking connection and they'll just wrap it 2, 3, 4 times. They're actually probably not solving the problem, making it more difficult for the fittings to get a good connection because they've introduced too much material between the points where it should be sealing. Again, use the right tape and use it sparingly. Protect the calibration standard. So inspect it regularly. Protect your pump with a case during transportation. You've spent a bunch of money on a good pump. Take good care of it. Keep your cleaning materials that you would use to clean your device under test or clean the pump itself. And spare pumps, keep them with the pump. Use filters and liquid traps. Up in the top right-hand corner is just a little picture of an inline filter. It's not fancy. It's just a filter that Fluke sells. There's other ones that are commercially available, but if you use a filter in line with your system, it'll just give you that extra layer of protection to keeping your equipment from being contaminated. And if you have any internal filters, we sell some equipment that has internal filters, and they sometimes get forgotten. So take a moment to inspect those internal filters on a regular basis and have spares available if you do find that one's not in good shape. It's worth changing out at that time. All right, let's talk about some exercise here. When you walk up to say for instance, a pressure device, it's intended to measure 100 psi, and it does it all day long. There may be some small fluctuations in that pressure. But the device itself has been scaled from 0 to 200 psi because that may be at some point in time what it's intended to maybe measure. But it spends 99% of its life sitting at 100 psi. It's important to understand those types of situations because all pressure equipment has some mechanical to electrical or mechanical to mechanical conversion, like a board on tube driving a dial on a gauge, or a diaphragm that's driving an electrical sensor to give us a 4 to 20 milliamp output. But there's always a mechanical element in the front part of it. And most mechanical elements will have some what we call mechanical memory. They don't want to necessarily move or change. So we recommend that you cycle it 3 times as a minimum, up and down, so that you give the opportunity for that device to kind of stretch to its maximum and back to its minimum. The final comment here at the end is the calibration that you do on your particular device should be representative of the actual usage. So if I were to say, use that example where I'm going to go across a 5-point calibration on a pressure transmitter that's scaled from 0 to 200 psi, normally you would think, okay, 0, 25, 50, 75, 100% of span. But if I'm never going to use what they correspond to, it might be easier to consider, well, what is my actual operating range? And say, for instance, it goes from 85 to 115 PSI. Maybe it makes more sense to do a 0, 85, 100, 115, and 200 PSI span as calibration. These are all surrounding what they call cardinal points. And if you want to do calibrations like that, it's very easy to do. It's just a case of writing procedures that more appropriately match the actual application. All right, this is a unique tip that we have. If you have any old analog gauges, they may be actually super accurate gauges like the one that's shown on the display there. They'll have individual markings for what the pressure is. And the question is, if I walk up and I pressurize this gauge, and say, for instance, I put 100 PSI on it, it's a nice round number to use. I put 100 PSI on it, but the gauge is not pointing directly at the 100 needle. It's somewhere between 100 and 101. And I'm not quite sure what number to write down. One of the tricks that you can do is make an adjustment on your pressure source and bring it down so that your needle points right at the 100, and then record what the source value is, which assumably would be slightly less because you had to bring it down. So that sourced value will be, again, initially more accurate than the actual gauge that you're calibrating because you've brought the right equipment to it, and you've been able to document what that actual value was that you sourced to generate 100 PSI. Rather than going the other way around and where you're generating 100 PSI and then guessing at what the value is on a gauge. I think that's a good way to approach things, and it's kind of a unique trick that if you haven't considered, it's worth considering. All right. One of the last tips that we have initially on this particular section of the presentation is to consider the electrical portion of your calibration. You may have most people look at the pressure calibrator from a pressure accuracy perspective because they want to make sure that they have the right, 4 to 10 times more accuracy, and they will not intentionally, but maybe not look at the other side on the 4 to 20 milliamp side, especially if it's a self-contained unit. If they had a pressure gauge and a hand pump and then a process meter like a 789, they'll consider the process meter accuracy because it's independent, but when it's together, they may not consider that there's an electrical portion. So just keep that in mind. And it's always convenient to have those two pieces of equipment in one. You take one piece of equipment to the field, not two. Just pay attention to that part of it when you do your calculations for how accurate everything is. Finally, when you have the opportunity, try to document your calibrations. This isn't just a comment because we have documenting equipment and we want you to buy them. From a user point of view, if I'm walking out and I'm doing a calibration, I may have a pump, a pressure source, like a standard that I'm measuring. I may have tubing, wrenches, fittings, tape. I'll have an electrical device that's going to provide, potentially 4 to 20 milliamps and make a connection on that side and make some measurements for me. Maybe a multimeter to do some switch testing. I may even have to take a communicator in the field. The more pieces of that equipment I can combine into one and allow me to potentially do the documenting as well will make me just that much more efficient. I won't have multiple things to make connections for. When in the field, if I had to take a pen and paper on top of all that other equipment, write down numbers, the 8 that looks like 6 or the 7 that looks like a 1, those type of transcription errors just won't happen. They're all done automatically and electronically in the device itself. The other really nice thing is I can potentially use this equipment to connect to software and generate automated calibration reports, where at the end of the day, all I have to do is fill in a little bit of information and sign off on the paperwork, and my traceable calibration is complete. Alrighty, let's talk about some technology for workflow improvements. Fluke has a application note. It's available in the sidebar, and you can download it directly from us today during the webinar, and you're welcome to grab it. You will find this is a complete list of everything that's in that. We don't have time to go through all of these today, but there's some really great tips and tricks above and beyond this webinar today as to how to deal with different applications and maybe some potential solutions. I want to take a few moments of your time to run through a few of them. I've highlighted these, and hopefully they will cover off the majority of what it is that you do on a regular basis. I will not necessarily be going through all the steps one by one and how to do something. I'm just going to talk generally and then make reference to the tech tips on each of these. So what we have here is a manual pressure switch test. The pressure switch itself may be a wet connection test, which means it's connected to an electrically live system and measuring, say, for instance, voltage on off, that kind of thing. Or it might be dry where it's disconnected. Either way, the connection is pretty much the same. If you take a look on tech tip number 2, we recommend that if you're making a connection to a wet contact, that you understand the electrical part of it, and be sure that the equipment that you're bringing to it, the multimeter, whatever the case may be, is rated for the correct voltage. When we come up to a switch, we are going to want to know what that switch point is expected to be. Again, just like exercising before, cycle it up and cycle it down, and then start to do a measurement where we capture what the set point is. Then we will back off our calibration point and find where it resets. And the difference between the set point and the reset is what we call a deadband. We're going to want to document what that deadband value is, and then cycle through that particular 2 or 3 times to make sure that we have some continuity between them, and the switch itself is switching on a regular basis. Depending on how you've set up your process, you may want to capture the maximum value for that set point, the minimum value for that set point, or the average of those set points that you've measured. And that will typically require that you've gathered a bunch of data and you're going to go do some analysis afterwards. But the process to go through this is pretty simple. Finally, the final tech tip number 3 down there talks about using one of our documenting calibrators to do switch testing. A lot of people will buy, for instance, a Fluke 754 or one of our other automated calibrators like the 729, and they won't necessarily know that we have pressure switch testing capability built already into that unit. They may be using it for, I've seen some people use it just for one particular type of calibration all the time, when in fact it's like a fire truck. It has all kinds of different capabilities, and pressure switch testing is just one of them. So if you have a device like that, we actually have pressure switch testing application notes available on the website from Fluke. You can also come back to GTS and they'll be able to help you out there as well. Heart Smart pressure transmitter calibrations. This is one of those things where if you come at the problem, you'll need a pump, you'll need a pressure gauge, you'll need a communicator, you'll need something to measure the 4 to 20 milliamps, you'll need wrenches. It becomes a little bit tricky in terms of all the equipment you need to bring to it. I'm not going to go through how we do this calibration. It walks you through pretty quickly on our application note in the 754. What I did want to do is highlight a couple things. And tech tip number 1 is not exclusive to this particular type of calibration procedure, but it suggests that you take any time you have maybe to check out your connections in a shop environment before you head out, just to make sure everything's working correctly, you don't have any leaks, things like that are eliminated. It's nice, it's convenient, it's warm, it's easier to deal with. If you take that same equipment into the field and you do have problems in the field, you'll know that it's field related, not equipment related, and you may be able to adjust that part of the problem. Another comment is written there is that pressure transmitters typically have some built-in delay. The reason they do this is pressure fluctuations. They don't want those fluctuations to filter through the 4 to 20 back into the plant, and that the plant begins, cycling. So they'll build in some delay, maybe make one measurement every, 10 seconds rather than every second. And the reason that they do that is, as mentioned, they don't want this problem. But when you come to do calibrations, you're going to want to know what that delay is, so that your device and your calibration procedure will match and give an opportunity for the transmitter to settle down. If you had captured values too quickly, you may be capturing erroneous values and thinking everything is fine. Alrighty, the next application that I want to dive into is, on the surface, it may be fairly complicated, but I'm going to break it down for us here. This is a custody flow computer calibration. And what we're doing here is we're actually doing one, two, three, four different calibrations or four different types of the calibration at once. So let's walk through each one. What we have on the display here, on this image right here, just so you know, this is a Fluke 721. It's actually a dual pressure. It typically has a low pressure and a high pressure port. It has a connection for a RTD probe, and it does the electrical connection. So there's a lot of stuff going on over here. What we do on a flow calibration is we need to measure a low pressure static value, low pressure differential value. And the way we do that is you have a hand pump to generate the value into the computer, and we measure back what that value is and do a closed loop calibration on that part of it. Each manufacturer has a different specific set of test procedures, so I'm not going to dive into the procedure side of it too much. This is just a general example, and we always recommend you follow the manufacturer's methods. At the end of the day, you're doing a low pressure calibration, and having that device available to you, like a 721 and a low pressure source, is good. I did want to highlight, I don't know if you noticed it popped up on the display here when I changed the screen, but these older style bicycle pumps that have been around for almost at least as long as I've been around, so call them 30 years, they're great at doing these low pressure calibrations. The biggest advantage to them is they don't generate a lot of pressure, like maybe 100 psi, but they have a really long vernier control. And that vernier control allows you to get a great adjustability, and the pump itself has a fair bit of volume in it, so you have a lot of opportunity to control the volume and therefore the pressure of a low pressure calibration. So even though they're not expensive, they're still maybe potentially a preferred piece of equipment over this type of pump that is a pneumatic pump, but is intended to work maybe as high as 600 psi. So it sacrifices a bit of that adjustability for the higher pressures. So in these applications, I recommend potentially changing out this pump for that in the image. A couple of tech tips to take away. If you're doing pressure calibrations, low pressure calibrations, and you are in an environmental situation where maybe it's sunny and then the clouds are blowing by and then it's sunny again, and you're starting to look at pressure starting to fluctuate, it's pretty amazing how little solar energy it takes to change the temperature of tubing. So rather than using a black or a darker tube, maybe consider using some clear tubing or something that maybe is not going to absorb that solar energy and then change the volume internally too much. Okay, what's the next slide? Static pressure. Okay, this particular image, we use one of our 700G pressure gauges to show static pressure. Again, static is what is the pressure in the system. We're not measuring the flow at this point, and we're just measuring what is the pressure exerted on the surfaces, and that's what this gauge is measuring for us. We didn't really need to show this. This is not an extra piece of equipment you need to buy. If you had a 721, this high pressure port would typically be able to measure the static pressure for you. Just be aware that the connection for the static pressure, try to take it away from the manifold and down on the line if possible. Sometimes manifold pressures are reduced volume, and there may be some restrictions in there that create errors in making measurements. So take it over if possible, take it as close to the line as possible. And again, just like we talked earlier, the pressure transmitters themselves have some time to respond, so just give it time before you take your measurement points. The final measurement is for temperature. We had a whole dedicated session on temperature similar to this on pressure probably about 3 weeks ago. And it was a full detailed discussion about temperature calibrations. This particular calibration, pretty basic. What I did want to point out is that it uses an RTD. So RTDs have very narrow, typically lower temperature ranges than thermocouples, but they do offer significant improvements in accuracy over a thermocouple type measurement. In this application, an RTD is probably enough for the accuracy of this flow computer. If you wanted to, Fluke sells PRTDs or SPRTs, which are, again, moving up that chain of traceability, a little bit more accurate, and they're still handheld and portable devices. And the reason you would be mostly concerned about making accurate temperature measurements is that directly ties to volume. the volume of this material is very, very closely tied to the overall temperature. If you've pumped gas at your gas pump, you'll notice that it has a calibrated to a specific temperature. And as the temperature changes, it changes its calibration for how much fuel you're buying. That's the same kind of thing that's happening with these custody transfers. Alrighty, let's go back to a very simple and basic way to do calibrations. If you have the opportunity to take your device under test and bring it back to a shop, there's plenty of options there for making clean, very readily available and easy to work with calibrations, as opposed to packing up gear and taking it to the field. This particular person is doing something with a very simple gauge comparator. So what you do is you have a high accuracy pressure gauge as your reference standard, and you compare it to your unit under test, and you have the ability to turn this wheel and make adjustments for pressure and then some vernier adjustments, and you're constantly making a comparison between the two. Again, probably one of the most simple, easy ways to do a calibration. And the nice thing about them is they're not super expensive. So if you have the opportunity to do calibrations like this, it actually might save you a bunch of time. If you have, like, say, for instance, gauges like this in the field, you could calibrate one, take it into the field, do a swap, and bring the gauge back and do a calibration and put it on the shelf ready to go. It would require more equipment, but it would allow you to rotate your gauges and keep your process up and running and provide for calibrations on a bench type environment. Okay, let's talk quickly about some real customer feedback pain points, and it's typical of pressure calibrations. So we have customers that are, constantly trying to deal with pressure leaks. We have people that are, how can I possibly do documenting when my hands are already full? Even documenting with a pen and paper becomes a bit tricky. Generating accurate pressure stability, across an entire calibration range can be difficult. And if I have multiple point calibration, that means, every single one of those points I have to weight, stabilize, and do a calibration point. Testing pressure switches, again, this is just a kind of prelude to this product that I want to introduce to you. So the Fluke 729 is a automatic pressure calibrator. It's been out for about 4 or 5 years now. If you had an opportunity to buy one or see one in action, they're pretty amazing. Ultimately, what we've done is we've taken a hefty lithium-ion battery, put it in the device. We have a pressure pump and a pressure controller, that same kind of pressure controller technology we have on the bench, and we are able to drive, depending on which model you pick, there's a 30, a 100, or 300 psi. We're able to drive pneumatic pressures into systems and automatically measure 4 to 20 milliamps, and this little orange button there is a heart communicator. So it's got a built-in heart communicator. So now we're talking, measuring 4 to 20, and doing automated calibrations by making literally 2 connections. We're making a pressure connection and we're making an electrical connection to the DUT. It can be a little on the heavy side. I think it weighs in at around 8 or 9 pounds. So we've come up with a 2 magnet solution in this Y configuration that allows us to hang it on anything metal. It also has a tilt stand and then a shoulder strap, and there's a bunch of other ways to deal with this product. But anybody that's used something like this already, they're finding that there's anywhere between 2 to 3 times not only accuracy and improvements in data collection, but in terms of overall speed. So if you have a lot of calibrations to do, say for instance coming into a turnaround, or you've got a new project you're doing, having that kind of speed and accuracy in a handheld device will easily pay for itself in terms of how quick and fast you can do calibrations. If you own any Fluke 750 pressure modules, which are external pressure modules that we use for higher pressures, you can still use a hydraulic pump and this device with a pressure module and automate calibrations and document them using this. Enough of the sales pitch. I just wanted to bring it to your attention. It's probably one of the more exciting technological improvements on pressure calibrations that's been available for industrial. Okay, we're coming up on 45 minutes in the presentation. I just want to take the last couple of minutes to run through a couple of points and just highlight them for you again. So Again, pressure calibrations are valuable to your operations, and getting the right piece of equipment for your workload and applying the right gear for the application is critical. When you misapply equipment, it becomes a source of frustration and or potentially poor calibrations. Understand the potential sources of instability, and in your particular case, try to find ways to mitigate that. Again, resolution is a balance between accuracy and resolution, so try to find a way to strike that balance wherever possible. Take the time to clean up any systems that you're dealing with and avoid contamination wherever possible. It doesn't take much to get back into a pump and then eventually destroy it over time. Exercise your pressure equipment prior to calibrations. So if you have equipment that you know doesn't necessarily move a lot in pressures, take a few moments to run it up and down the span a couple of times and then do your as found. Be engaged with the potential for improvements in your process. That's obvious. You're here sitting in on our webinar. We want to thank you for that. And consider the advantages of any ways to make improvements to that, either with new equipment or through automation, tips, tricks. We have videos on our website. GTS has more than enough information to help you make a good decision with regards to your next challenge. Take a look at software. The world is really moving towards a documented world. There's not just pressure, there's all kinds of other applications out there that drive us from maybe being a PM type program to a predictive maintenance model. Pressure doesn't usually get seen as a part of that predictive maintenance, but if you have software and documentation and you can make that easier, Fluke is migrating heavily on that side of the business. Where it makes more sense, get a set of pressure calibration for gear for the shop. And again, seek training, ask for help, come after us for knowledge, technology. We like to consider ourselves measurement experts, not just for pressure, but for the other products that we do. And feel free to bring us your problems. We'd be more than happy to help you, let you know where we are today and what technology is available to help make improvements. That's it. That's all I have for the presentation so far. I hope you found it valuable. I'll toss it back to Chris.
Thank you very much, Ken. Yes, thank you very much for the presentation. A lot of information. I know that we covered a lot of different topics. We have just over 10 minutes to get to any and all of your questions, so I encourage you to use the chat feature. We did have a few questions come in during the presentation. I did want to just touch upon getting any and all questions that you may have post webinar. Given the amount of information that we've covered, maybe not everything will come to you right now. You can visit our website, globaltestsupply.com. You'll find the list of products that Ken touched upon today, all calibration type of products under Fluke, pricing, availability, technical data sheets, manuals, and most importantly, to get in touch with one of our technical sales staff, like myself. You'll have our contact information via phone, email, and chat as well. So once again, please use the chat feature. Take advantage of us having an expert like Ken with us today. So let's see. What would be the recommended calibration interval for these types of equipment, Ken?
Okay, calibration intervals have a lot to do with the risk that you're willing to take. The idea is that manufacturers typically will specify 1-year recalibration cycle. There is some statistical numbers behind what decisions you make. If you have critical processes, you may be more interested in having a 6-month calibration. Less critical might be 2-year calibration. Ultimately, it comes down to what risk are you willing to tolerate if your standard is returned and it's out of calibration. If it winds up being out of calibration and you're on a quality program, it can be pretty expensive from a time perspective to work back through your workload in reverse order to make corrective actions on calibrations that may have been done out or done out of calibration by that bad standard. Recalibration, again, a 1-year calibration cycle is typical. And we have some equipment, some of our pressure modules have a 2-year specification. If you choose to go to a longer standard, you should probably make those adjustments for your overall accuracy. So extending your calibrations will lower your accuracy of your standard. Yeah, I don't know if I've probably covered off everything I need to on that. If there's any other questions, I'd be happy to answer, but it's typical, follow the manufacturer and use a company like GTS to do your calibration services.
So good segue into our next one. These types of calibration equipment, would they replace calibrations offered by companies like ourselves, or would they kind of work hand in hand depending on, I guess, a customer's exact application and the instrument that they're using?
That's a good question. I'm going to double back to one other part of the slide of the presentation again. So we have this, getting close to the beginning here, I don't want to go too far. There we go. So you should see the calibration traceability pyramid. These process instruments out in the field, that's what you're calibrating. What you're taking to it is a working standard. As long as you can maintain these 4 to 10 steps between what you need to calibrate, then you can be okay, but the price goes up significantly as you go up these steps. As you know, your process instruments, let's pick a 1/4% gauge, you can probably buy it for a couple $100. If you want to be, 10 times more accurate, now you need something with a 0.02% accuracy, and now you're starting to talk about a couple $1,000 type piece of equipment. Imagine taking it to that next step, and you'll probably have to put a 0 at the end of that number to try to figure out how much you spend to get these accuracies, and all the way up through the standards levels. It all comes down to doing math. The interesting thing is the higher you go up the standards, there's all kinds of other factors that come into play. Temperature coefficients, some of those pieces of equipment are just not built to be field ready. And owning a primary standard like a deadweight tester in a shop to simply calibrate your own test gear might be overkill and more expensive than it's worth. I don't know if I just did a big, huge sales pitch for GTS, but that's my take on it.
Oh, we'll take it. Okay, so just a quick reminder, if you do have any questions, please, we have about 5 minutes left before we sign off today. Please use the chat feature. So another question that came in that is pretty typical, and we get a lot as well. Most customers will have more than one gauge, different ranges in their gauges. So as an example, would you be able to use the same type of calibrator to calibrate a 10 PSI gauge and a 300 PSI gauge?
That's a good question. We have, it comes down to the way that the equipment is specified. The overall accuracy can be specified in so many different ways, and it's typically done to make equipment look good on paper. It's what we call banner specs. When you dive into the actual calibration accuracies, you'll find that there's 2 typical ways that they get specified. One is percent of full scale, and the other is what they call percent of reading. If I had, say, for instance, that 300 PSI gauge, and it was spec'd at 1%, 1% full scale, that would mean I'd have 3 PSI on either side of 300 would be 1%. So anything between, well, I'm doing my math here, 297 and 303 PSI would be considered accurate. If that's my full scale accuracy, if I take that all the way back down to, I think you said 10 PSI, that plus or minus 3 comes into play, and now it's significantly poor at 10 PSI. If I had it spec'd as percent of reading, that accuracy might be, higher than 1% of reading. Say it's 2% of reading. At 300 PSI, that means, it's 300 plus or minus 6 PSI, but down at 10 PSI, it's 0.2 on either side. And so understanding your accuracies and how they play with each other across a range is important. I guess the takeaway is it might not be able to, it could do it. It really comes down to doing the math. And I really recommend you take a few moments to confirm those accuracies, especially if it's a critical measurement. Try not to misapply equipment. Typically, a 300 PSI piece of equipment is generally not intended to work below, say, 3 times its range. So below 100 PSI gets a little bit questionable. Same thing with a 3000 PSI, might be a little bit questionable at 1000. It just has to do with specifications.
Absolutely. And just to add on to that, if any of you do have questions specifically related to specific products, accuracy of those products, kind of, trying to decipher through the technical data sheets, we are here to help you. Our technical sales team is here to help you. You can go on our website, globaltestsupply.com, the contact us page. Again, you can find a full list of products, pricing, availability, data sheets, manuals, all on our website. So one last call for questions via the chat. While we wait to see if we have any last minute questions that come in, I'm going to thank you once again, Ken. Absolutely fantastic presentation. As I mentioned before, lots of information. So, I'm sure a lot of you do have questions. If we don't get to them, please contact us by visiting our website so that we can address them privately and after the webinar as well. So it doesn't look like we have any more. So Ken, thank you very much.
No, you're welcome. Thank you. Thanks everybody for your time and attendance, and I appreciate your time.
Yeah, to respect everyone's time today, we will sign off today. So on behalf of Global Test Supply University, we thank you very much for attending today's webinar. We hope you found it informative and very helpful. We are available to assist you in any way. As I've mentioned a couple times, please visit our website, globaltestsupply.com. For anything you need through our website, you can find our entire list of Fluke products with descriptions, specifications, pricing, availability. You can check out our rental page, our calibration services as well. And you'll also find our contact information to get in touch, as I mentioned earlier, with one of our technical sales staff via phone, email, and chat as well. At the end of this webinar, we have a short survey that we'd like you to complete. Your feedback will assist us in improving and allowing us to bring you more topics that are of interest to you. So please take a moment to do so. We also have a few upcoming webinars over the next few weeks and months. You can visit our training section of the website to find a full schedule of upcoming webinars and topics. And don't forget, as a thank you for attending our webinar today, your name will be entered in a draw to win $100 towards your next online purchase. The winner will be announced on our social media channels, so please be sure to check us out there. Ken, once again, thank you very much, and thank you everyone for attending today. We wish you a great rest of the day.